Hello everybody. In this video, we'll learn how to calculate a line of best fit. Now, what does that mean? Well, the goal of this little investigation is to find the equation of a line, and I'm going to use the traditional format of the equation of a line, y equals mx plus b, that is the best fit for a set of data. So, for example, imagine you're given some data represented by these blue points here, 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 and here. It's not possible to draw a single line which passes through all of those points. What you can do is you can draw a line, which I've drawn here in purple. You can try to find a line which minimizes the sum of squared errors. In other words, what that means is draw this line, and then at every x value, right, draw a point corresponding to the x value of a point in your actual data set. Now, each one of these red points right here on the line, right, they're a certain distance away from these blue points. The red points on your line, you can think of those as estimated data. You're trying to estimate these blue points right here. You can tell how close you are by calculating the error, which is represented as these dashed lines, these vertical lines right here. And so, right, what you can do is square these values, then add them up, and you want that to be as small as possible. One thing you might wonder, why square the errors? Why not just add the errors together? The reason we typically square the errors before we add them is sometimes you'll get a negative error, and sometimes you'll get a positive error, right? Depending on whether the line is an underestimate of your actual data or an overestimate of your actual data. If you just added positive errors and negative errors together, they could cancel out and mislead you into thinking there's no errors, right? And that would not be correct. So if you square the error terms, then that removes any negative signs, right? And also, an added bonus to squaring the errors rather than just, say, taking the absolute value, right? This will mean a small error, an error less than 1, actually becomes smaller and less relevant, whereas large errors, right, if your error is 2 or 3 or 4 units, you'll get penalized a lot more for that. So this is a standard technique in statistics to try to minimize the sum of errors, the sum of squared errors, when you're coming up with this line of best fit. So the big question is, if you're given a bunch of data points, how do you find the equation of this line? Lucky for us, we can do it with matrix algebra. Let's assume we've got an actually easier case to start, just for illustrative purposes. Let's say you're given 2 points. You can find the equation of a line that goes through 2 points. And this might have been something you did in an algebra class back in the day. But let's see how we would do this with matrix algebra. So we want to find the line of exact fit, right? The equation of a line y equals mx plus b, using matrix algebra. Let's say we have 2 points. The first point is 1, 1. The second point is 3, 2. We can take the values for these 2 points and plug them in. Right, be sure you plug in the x values in for x and the y values in for y. And now we have a system of 2 equations with 2 unknowns. I want to take those equations and rewrite them in a slightly different form. Right, so I have something times m plus something times b equals a constant. Right, that's a system of equations. In matrix algebra, we do like to write things as matrix equations. So I could gather the coefficients into a coefficient matrix, gather these variables m and b into this vector, and then the constants into this vector. It does seem kind of weird, right? In that m and b, we're thinking of those as the variables. We normally think of x and y as the variables. But in this case, x and y, those are constants that are given to us, right? So in this case, what we have is the unknowns are the m and b that we're looking for to find our line of best fit. So how could we solve such an equation? Right, there's a bunch of ways we can solve it. You could use an augmented matrix, all sorts of things. And what I'd like to do here is to use an inverse matrix. Right, find the inverse of this matrix A. Right, this is A inverse right here. 1 divided by the determinant, that's 1 minus 3. Right, swap these numbers and put negative signs on these numbers. Here's your inverse matrix. Then to solve for V, V is equal to A inverse times W. Right? It's like multiplying both sides of this equation by A inverse to cancel this out. And V is equal to A inverse times W. So we just have to multiply A inverse times W. I usually like to leave the fraction out front and then scalar multiply that in at the last step. You could multiply this matrix times this vector, then multiply the resulting vector by this scalar. Coincidentally, in this example, m and b both happen to be 1/2. Right? Actually, that looks about right. Right? Y equals 1/2 x plus 1/2. So your intercept is about 1/2. And then you go over 1 and up 2 and over 1 and up 2, and that'll pass exactly through those 2 points. Hey, so that's the line of exact fit. But what if you have 3 points? And let's say we want to go through the same process. Right, the first 2 points as before, but then a third point right here, the point 4, 1. You can tell just by looking at this picture that no line's going to pass through these points. They would have to line up perfectly. In terms of matrix algebra, we could go through the same process as we went through before. Plug these values into the equation y equals mx plus b. In this case, you have 3 data points, so you have 3 equations, one corresponding to each data point. Go ahead and rearrange those equations, and then you could rewrite this in all sorts of ways. I also want to bring back to your memory vector equations. Right? We could write this as the vector of coefficients of m times m, plus the vector of coefficients of b times b. Right? In this case, this is always going to be a vector with just ones, equals the vector of these values. Or you could group these 2 vectors into a matrix and group these 2 variables into a vector, write it as a matrix equation. But really, no matter how you write it, we know, just based on this picture, there's going to be no solution. Now, before we talk about finding the best approximate solution, I want to take a trip down mathematical memory lane and remind you of some calculations that we did once upon a time. Right? So one thing we used to do when we first started learning about points and vectors and lines and planes, we used to find the distance from a point to a line. Right? For instance, here's an equation of a line, just made this one up. Let's say there's a point not on the line. How do you find the distance from the point to the line? Well, we would find the closest point on the line, and then we would measure the distance of the segment between these two. Now, the closest distance is always going to be the distance or the length of a perpendicular segment. Right? To measure the distance from this point to this line, you're not going to pick some point way out here and then measure that distance. Now, the closest point always forms a perpendicular segment. It's the same thing when we went up a dimension and started talking about points and planes. Right? Remember, a plane is an infinite flat surface. Right? To find the distance from this point Q to this plane, you would find the closest point, and the line segment, the vector, between these 2 points is going to be perpendicular to the plane. And so keep that perpendicular in mind. Closest distance, that's going to result in a perpendicular vector to your plane. And also, as a side note, there's lots of ways you can write down equations of planes. Well, by lots, I mean 2. And in this case, we're really actually going to use this form of the equation of a plane. It turns out to be slightly more helpful. Right? This is writing the equation of a plane as a vector equation. Now, you can think of the plane as kind of a generalization of the equation of a line, except there's 2 variables, right? A vector times its first parameter plus a vector times its second parameter plus some kind of a base point on your plane. Right, so it's like starting at this base point and then you can travel some combination of these two directions. Again, these numbers are just for example. They're not really relevant to the problem we've been looking at so far. And is it all coming back? I hope. Now let's go back to our original question. Right, our original example, let's take a look at the vector form equation. I have a vector times m plus a vector times b is equal to a vector, and we know that this has no solution because there's no line passing through those 3 points. This has no solution. Let's give these different parts of the equation names. Let's call this first vector v. Let's call this second vector w. Let's call this last vector q. And I'd like to think of it as a point more than a vector. Right? So I'm using point notation for this last one. These two vectors, let's think of those as the columns of a matrix A. And so we also talked about writing this as a matrix equation. In this case, it would correspond to the matrix equation A times the vector MB is equal to Q. And again, even if it's written in the form of a matrix equation, it still has no solution. Now, what I'd like to do is I'd like you to think about a particular plane. In this case, I've got an equation of a plane. Instead of using t and u as the parameters, let's use m and b. Right? Consider the following equation of a plane. Vector v times m plus vector w times b plus, here's your base point. I'm just using 0, 0, 0 as the base point. This is the form of the equation of a plane. And for example, or in particular, I should say, right, this plane is actually the set of possible values of the left-hand side of this equation. Right? All the possible values form a plane in three-dimensional space. However, this point is not on that plane. Right? This equation is never equal to Q. We've been saying that again and again. This has no solution. Q is not a point on this plane. So what's the best thing that we can do? Right? Q is not a point on this plane. Q is not a solution to this equation. However, we do know how to talk about possible points that are close to a plane. And so looking back at our previous slide, right, we have a plane, right, so it's a set of possible values on the left-hand side of that equation we just saw, and we have a point not on the plane. We're interested in finding the closest point. So let's just call R the closest point on this plane, the closest point to Q. Well, if R is on this plane, right, then A times the vector MB equals R, it does have a solution because it is on this plane. Whatever that solution is, we'll just call it U. So that's going to be two specific numbers we're going to try to solve for. So the matrix A times the vector U equals the point R. Right? So AU is equal to R. AU is approximately Q. Right? Why am I saying approximately here? Well, R is close to Q. If A times U equals R, and R is close to Q, well then A times U is close to Q. It's approximately Q. And in particular, this is what we're going to want to solve for, right? We want to solve for these values that give us the closest solution. This is our best fit solution, the best values of M and B that we can find so that we get something close to Q. So that's the goal, to solve for U. So now we have to ask ourselves, how do we solve for U? Right, so here's the idea. Here's a picture of what we were looking at before. Right, we have our equation of a plane P. We have our point Q, which is not on the plane, but R is the closest point. Right, so if we form a vector between these 2 points, Let's call that vector s. S is equal to q minus r. We know that vector has to be perpendicular to this plane. If it's perpendicular to the plane, then it's perpendicular to all the vectors in the plane, which includes v and w. Well, if this vector s is perpendicular to v, then v dot s is equal to 0. And since the vector s is perpendicular to the vector w, then w dot s is also equal to 0. So we get these two equations. Let's go ahead and combine those two equations. Let's write them as a vector. And so v dot s is equal to 0, w dot s is equal to 0. Right, so the vector of these two values is the 0 vector. Now, because this has a lot of dot products in this, you know that matrix multiplication must be lurking in the background whenever you see dot product calculations. So this expression is really the matrix whose rows are v and w times the vector s. And that's equal to the 0 vector. So I'm just rewriting this equation so it looks like a matrix times a vector. Now let's remind ourselves of this matrix containing v and w. If we go back to our previous slide, remember we defined this matrix A to be the matrix whose columns are v and w. Right, so since the columns have become rows, this is actually A transpose. And the vector s we just defined as q minus r. And so substituting those in, we have A transpose times q minus r equals 0. Well, what is r again? Yeah, r is equal to A times the vector u. So we'll substitute that in. Then I'll distribute through the A transpose. So A transpose times q minus A transpose times A times u. And distribute that through. And then move the A transpose times q onto the right-hand side. It becomes negative. Multiply both sides by -1 so they become positive. And we have this equation right here. A transpose times A times u equals A transpose times q. Now the great thing is, this is a solution we can solve. Right? The whole point of finding r, or talking about r is a point where a solution exists. So u is guaranteed to exist. So what we want to do is solve this equation, and u contains the slope and intercept, the m and the b, that we need to find our line of best fit. So this is the equation we need to solve. It looks a little bit complicated, but most everything here is given. Right? A and q are given values. We'll calculate A transpose and multiply both sides by that. Then we'll get a solvable equation. All right, that's enough for theory. Let's actually do some examples and see how this calculation works. It is nice to understand where it comes from, though. Okay, so going back to our original example, we have this matrix equation which has no solution, and we know it has no solution because this equation corresponds to trying to find a line that fits through these 3 points. Just based on the diagram, no line goes through those points. So what we want to solve is this equation. I want to multiply both sides by the transpose of the coefficient matrix. So for the transpose, you just turn columns into rows. And we've got to multiply both sides by that. And then you've got a 2 by 3 matrix multiplied by a 3 by 2 matrix. The result is going to be a 2 by 2 matrix. It's pretty nice. Then when you multiply this 2 by 3 multiplied by a 3 by 1, you're going to get a 2 by 1. So this actually becomes a much more condensed equation. And this is an equation we can solve. Right? The way I like to go about this is calculate the inverse of this 2 by 2 matrix. It turns out to be 1/14 times these values here. I'll hold off on multiplying this through until the very end. But to calculate the values of m and b, right, we just multiply this vector times the inverse matrix. When you're done, you get 1/14 and 16/14. So 1/14 is your m, that's the slope of your line, so it's just sloping up just a teeny bit. And 16/14, that's your b value, that's your intercept. Right, so this is the equation of the line of best fit. In other words, you can draw this line right here. The y-intercept is a little bit greater than 1, and it's slowly sloping upward. Right, this is the best approximation that you can do for these 3 points. If you were to change the slope or the intercept a little bit, the sum of these squared errors is going to be larger. And again, this is a very useful kind of problem to be able to solve. It particularly occurs in mathematical modeling and data analysis and statistics. Right? You can thank matrix algebra for helping us solve it. This has one more example to show you that once you really get going with this method, it's pretty quick. To find the equation of the best fit line, y equals mx plus b, for this set of 3 points. Here the points are 2, 3, 4, 5, and 5, 7. Right, first, plug these 3 points into this equation. Make sure the x's and the y's are correct. And here's our y's are equal to the m's times x's plus b's. I always like to rearrange it before I write the matrix equation. And so I'll rearrange. Here's my matrix equation. A times the vector mb is equal to this vector of constants. And then we just need to multiply both sides by the transpose of A. And so put the transpose on both sides. Right, go ahead and do your standard calculations to find this matrix product. You'll end up with the 2 by 2 matrix equation. 45, 11, 11, 3 times the vector mb is equal to the vector 61, 15. And then you go ahead and calculate the inverse of this matrix. Strangely coincidentally, again, the determinant was 14. And it's not always 14, but it was in these examples. And so mb is equal to the inverse of this matrix times your vector of constants. And that gives you your slope and your intercept of the line of best fit. Right, in this case, the slope is 18/14 and the intercept is 4/14. And so not a very good picture, not really to scale. But here are our 3 data points, and I think if you start at 4/14, it's right around here. Your slope is just a little bit bigger than 1. I think it's going to pass through something like this. And that's how you find the line of best fit. In theory, you could have more than 3 points. You could have 4 or 5 or 6 or 7. Right? It's not too much more work to write out this matrix equation. It'll take a little bit longer to calculate A transpose multiplied on both sides, but at the end you will still get a 2 by 2 matrix equation. So this method generalizes very nicely. That's how you find the line of best fit. You learn math by doing math, so here's an exercise for you to practice this on. So here are 3 points, 1, 1, 2, 3, and 3, 3. You want to find the line of best fit through these 3 points. So you want to follow that same process that we've done for a couple of examples in this video. And when you're done, you should get an equation y equals mx plus b. I'd recommend you try graphing it just to make sure it looks approximately correct. There you go. Good luck with that. And that's how you find the line of best fit. Thanks for watching.